revise the syllabus, we will do a bit on clay mineralogy. So in clay mineralogy, I have in essence summarized, a bit by bit everything into 1 hour duration. I hope we can complete these 3 subtopics today. The subtopics are related to the sheet. So tetrahedral and octahedral sheet is something which is again something a basic fundamental sheet of which all the clay minerals are made of. These two are important for us. We'll also look at the difference between a structure and fabric, which is something which is a term which has come up in the last 2 or 3 decades. The difference between structure and fabric of a clay. Let's move on to the next slide, please. A bit background on what our talk is about. We are aware that sands, silts, I hope by this time some elementary understanding of particle size is known to you, as well as a bit on classification which perhaps would have been started or is likely to start, which will distinguish between sands, silts and clays. So the top two, which is sand and silt, is we have seen that the behavior, the mechanical behavior, meaning and the permeability, these 3 are important for us, are largely dependent on the particle size and shape. These 2 are important because greater the interlocking, well graded the granular material, you have greater strength, and vice versa for the soils which have which do not meet these conditions. Water to some extent over here has some role. The role of water is have some are affected by water, and of course we are aware that water has a capillary action to some small height above the phreatic level. So that capillary action also tries to change the behavior, the properties of the material. Coming back to the clay soil is complex. The reason being, I've listed 3 reasons. The first one is they contain clay minerals. Clay minerals are logically the most important characteristics which make this material a lot different. It has plasticity, as the minerals and plasticity. In fact, all the 3 are quite related. So mineral plasticity is another characteristics which makes them unique. And the last one, which I've quote unquote put in quotes, is cohesive. We all call this clay soils as a very crudely we call them as cohesive soil. Now for last 2 or 3 decades, that's about 30 years, people have started to realize, there's a small group of very strong, researchers who have started to realize I call clay as cohesive, but I can also do a test on sand, an undrained test on sand, and just get a cohesion value. So the cohesion value of just a pure sand, meaning I do an undrained test, call it an undrained traxial test on sand, and I can get pure cohesion. So in other words, can I also call sands as cohesive because it's pure cohesion? So that group of people is now very strong today. So they have a very strong feeling that we should not be calling clays as cohesive. Although our teachers, our teachers and everyone, we have been only calling clays as cohesive. But today, a lot of international standards, look at BS code, they have changed. They don't call clay as cohesive. They call them as fine-grained plastic soil. So this is something perhaps over the period we will try to change or adapt to the new system. Coming back to the below thing, it says these are evolved from primarily from chemical weathering of rock. We have done this, and even a small amount of clay. For example, if you have clay clay around 30% or so, it does make a significant difference in the property of the soil. All the other particles, in fact, start to float. Even if clay is 30%, start to float in a matrix. and we do call it as clay material. Even the clay is less than 50%. Move on to the next slide, please. So the clay minerals, the first few words are pretty important. They are hydrous. So let's break them up. Hydrous meaning they have water. Okay, alumina, and silicates. Silicates is the major component. So they have both water, hydrous, alumina, and silicates. So these are the important components. Plus other metallic ions are maybe present. For example, manganese. So they consist of crystal sheets, and crystal sheets are stacked on one top of each other. So even if we say your clay minerals are visible in electron microscope, under an electron microscope you only see the crystal sheets. You're not able to see the exact whether we can see silica, alumina. No, we can only see the sheets. And we'll talk about these sheets in greater detail. The first sheet is the tetrahedral sheet. It's also called as silica because it has we call it as silica. The second one is octahedral or alumina. So we look at these two sheets in detail. All the clay minerals are made of combinations of these two. So you play around with these two individual sheets and you get a different clay mineral. So today we will speak about the sheet, the first one, tetrahedral or the silica sheet. As the name sounds, you have a silica at the middle. There is silica in the middle, and tetrahedral means it's a four-sided figure. So at the corners, four corners, you have oxygen atoms, and in the middle you have silica. So it makes a tetrahedron. That's a four-sided figure. Each of these four-sided figures are connected at the base. So we call this as base. They're connected at the base to make a sheet structure. So you can find these funny clown caps with with pointy towards the top. So that's tetrahedral sheet. Rather than as an engineer, it will be very hard a task for me to draw this if I want to speak about it. So as an engineer, we have a schematic representation of this sheet, which is shown by this four-sided figure. Four-sided figure. I think we call this as a tetrahedron. Tetrahedral sheet. I think it's called as tetrahedron, or I mean it's a four-sided figure. Let's call it a four-sided figure for the time being. Okay, so that's the representation, and you write silica in the middle just to show that there is silica in the center. Okay, so to summarize this, there's an oxygen atom at the base are connected at one plane, and the unjointed oxygen atoms all point towards the same direction. So if these are connected together, if I look at from the top, if I look at the top view, it looks like an hexagon. So in each hexagon, okay, where is the the writer thing, please? This one? Okay, that's red color. Okay, good, thank you. So this whole thing is like a tetrahedron thing, each tetrahedron. Can I make it red? I like red color. Okay, it's yellow. Okay, never mind. Yellow is also good. Okay, so that's a tetrahedron for us, and it's connected. If I look at the shape, which the shape it makes, it's a hexagon. So there's an empty hexagon gap in between. Okay, both of us are moving the mouse, so perhaps the mouse moves. Okay, so it's an empty hole. We'll speak about this empty hexagonal hole later. It's very important. That's why I try to identify the hole. Okay. Go to the next one, which is octahedral sheet. Octahedral or alumina sheet. Okay, that's we call this alumina because majority of the inner, instead of silica, I have now alumina. There are chances when this alumina is replaced by magnesium or iron. So we look at the case of magnesium later, but alumina is the major one. So at the center it's major, and outside you have either oxygen or hydroxyl. So that's OH or oxygen O. And because we call it an octahedral, so it's an 8-sided figure. Okay? So 8-sided figure meaning you just look at the shapes, sides, please count the sides, it's 8 sides. Okay? So 1, 2, 3, 4, 5, 6, top 7 and bottom 8. And each of these 8 sides, you can see that they're connected to make a sheet. So you have hydroxyls or oxygen interconnected from both from top and bottom to make a sheet. So this sheet, the representation of this sheet, okay, is shown by this four-sided figure, and I know this is called rectangle. So it's represented by a rectangle with aluminium as a schematic representation of aluminium in the middle. That's again how the top view will look like. And we're not going to draw this, sketch this, but for all engineers, we always recommend that you should at least know what is the schematic representation. So, to summarize these two, we say all clay minerals consist of two basic sheets: a tetrahedral, that's a four-sided over here, and an octahedral, which is 8-sided, and they're stacked together in a unique way to make different clay minerals. And we'll speak about some of the clay minerals in the next slide. The very first one is kaolinite. We'll probably speak about 3 or 4 clay minerals, the more important ones. There are of course dozens of clay minerals which exist around us, which are not so popular, but the most popular ones we'll discuss today. The first one is kaolinite. Kaolinite, just to give you a feel, is the white color clay. And if you work with, is this morning if you have brushed your teeth on a wash basin, everything is made of kaolin. Those wash basin and all is all kaolin for us. Or if you had an upset tummy anytime in the past, the syrup given is kaolin syrup. So that's the clay which we speak about. You drink this clay as well. It consists of one tetrahedral and one octahedral. So one tetrahedral stacked to one octahedral, and these stackings repeat an n number of times. So let's look at this stack very carefully. One octahedral and one tetrahedral. So if I'm able to show this clearly, so this one is a octahedral, that's a tetrahedral over there. So that's one particular set, and one particular set, I'm not sure if you can read this, it's 0.72 nanometer. That's the thickness of this particular set. So this particular 1:1 sheet or 1:1 crystal continues n times on both the directions. So you can see this. If I want to look at the correct representation, I have a tetrahedral. That's tetrahedral. Remember the pointy things are now on the other direction. These are the clown hats, and it's connected to the octahedral. So the bonding of OH from octahedral is now oxygen from tetrahedral is now connects over there, or hydrogen or I apologize, or oxygen from the octahedral connects to the oxygen over here. So it's common. So it gets connected, bonded. This bond, we'll speak about this bond sometime later. But look at the gap. So how this is filled out in between. This gap, we'll speak about this gap, is now is bonded together by hydrogen bond. Look at it, OH from there, and coming to the base of the tetrahedron over here. So that's the hydrogen bond which forms OH and H. Okay, this hydrogen bond is relatively strong, and it's not easy to break. Hydrogen bonds are strong, so if it's not easy to break, in the sense I cannot put in water in between. It's difficult to hydrate, and if it's difficult to hydrate, meaning it's difficult to swell, or difficult to keep them swell them, or to add one crystal to the other crystal, which makes them which enhances the swelling potential. So we'll speak about swelling potential in a while, but the purpose is, for this slide, I would like you to look at is there is hydrogen bond. Okay, if I move one step forward, I have another one, which is another clay mineral, which is also 1:1, and this 1:1 clay mineral is called as hellosite. Remember, our kaolinite is also 1:1. So one tetrahedral, one octahedral, same case for hellosite. So we can say it's related to kaolinite. It's very much similar to kaolinite. However, the sheets, rather than the sheets are quite different for hellosite. For hellosite, it's needle type, whereas for kaolinite, it's more of flaky, so flakes together. But hellosite, the crystal sheets are like needle. So these needles are formed because during formation of this clay mineral, the water seemed to enter in between the 1:1. So I have one tetrahedral, one octahedral, and one tetrahedral, one octahedral coming from the top, but in between I have water coming into picture. So if water came into picture during the formation of the clay mineral, that's hellosite. Okay, just to appreciate this, if water which has come in can easily be removed, so this water can easily be driven out, driven out even by putting in air, outside air, it's easy to drive out. And once the water is driven out, it's hard to push the water back in again because of the hydrogen bond which may have formed after the water is driven out. So in other words, if water which is chemically bound to the clay mineral is driven out, I have a different clay mineral or clay mineral altogether. This clay mineral altogether will have properties, I must say, similar to kaolin, because now it's no longer water exists. But if I am able to retain the water, I have a different property altogether. In other words, if I ask you to do liquid limit test, plastic limit test on this hellosite clay, I would not recommend you to put the sample in oven or put it air dry. I would have to use the natural water content to do the test. Otherwise, the results would be quite different. The third one is montmorillonite. We also like to call it as smectite. Okay, it's smectite or montmorillonite. To give you a feel of montmorillonite, if you have ever eaten Kit Kat chocolate or Mars or Snickers, they contain the sticky material which you feel which is very juicy. That sticky material is montmorillonite clay for us. Okay, it consists of 2:1, so it's 2:1 clay mineral. It has two silica, so that silica, the four-sided figure. Okay, I still need to think about what's the four-sided figure. And one alumina, that's the rectangle for us. Okay, so it has one alumina and this two four silica sheets. So it's called as 2:1. Look at this in detail. Okay, I hope you can see this figure. So it's a octahedral sheet. In between, that's the alumina sheet, a rectangle over there, which is sandwiched between two silica sheets, or it is sandwiched between two tetrahedral sheets. So it's 2:1. The height of this, or the thickness of this, is 0.96 nanometer. Okay, so previously I think it was 0.72. So you're looking at very similar, each crystal thickness 0.72. This is slightly greater to 0.96. So you have this combination, and this extends to infinity. If I look at one particular setup in detail, so that's the center one is my octahedral. Okay, 8-sided figure sandwiched between two tetrahedrons. So two 4-sided figure. That's the sandwich I have created. And one sandwich is connected to the other sandwich by weak van der Waals forces. We are aware, elementary chemistry tells us van der Waals forces are weak. They're easy to break off. Meaning it's so easy to break off, I can easily push in water in between. Water can easily be pushed in. If water can be pushed in, so this makes the clay very swelling. It makes the clay swell a lot. In fact, it's the highest swelling clay known to us. Okay, that's the extent of this particular clay. Okay, let's move on to the next one, please. The next one, okay, we've just said this. It's used in chocolate bars. And there's another example of usage of montmorillonite is the drilling mud. If you happen to do a site investigation, and if your borers are in soils which are easy to collapse, and you don't want to use casing pipe to stabilize the borehole, so sometimes this clay, montmorillonite clay, we call this as also bentonite, is the same thing. So that brownish color powder is mixed with water. So this clay is easy to help stabilize the borehole. So we call this as drilling mud. So drilling mud is is stabilizing, used for stabilization. So the next one which I just would like to mention is a Alight. Okay, Alight, in fact, probably comes because the people who discovered this, were from Illinois. So they probably thought, why not bring in the first few words. So maybe if you have your local clay tomorrow, you would like to label them or rename them as your whatever you fancy. So Alight is also a 2:1. It's also a 2:1, similar to montmorillonite. Okay, the only difference is this sandwich. Remember this octahedral sandwich between two tetrahedrons. So one sandwich and the other sandwich, rather than have weak van der Waals, there is a potassium ion which fits in between. So if I go back few slides back, when we introduced our tetrahedron, we said there is a hexagonal hole, and I tried to highlight the hole using the mouse. So that hexagonal hole is just nice to allow the potassium ion fit in. So potassium ion which fits in now holds on to the two sandwiches, and it does not allow the sandwich to swell. In other words, now the water can't enter in between. It's hard for the water to enter. So this difficulty of water to enter makes it less swelling. In other words, Alight will have less swelling potential than montmorillonite. So to give you an idea of swelling potential, Alight is in between montmorillonite and kaolinite. Right? So that's the the swelling potential range. Let me check. I have right clicked, and yes, you can download this file at your terminal. It's easy to download. Let me go to the next slide, please. Next one is a definition. It's a pretty important term, and whenever you would like to speak about clay mineralogy, you also speak about a specific surface. So specific surface can be defined as surface area to the volume. So it's ratio. It's not a ratio. It's a specific area divided by volume, or a specific area divided by mass. So you could use any one of these two definitions. It's still specific surface for us. The important thing is, the smaller the particle, the greater the specific surface. Okay, give you an example. So smaller the particle, greater the specific surface. The example is given by a cube. Let's look at a cube whose each side of the cube is 1 centimeter. So please look at the first line over here. So it's one cube you're looking at, and each side of the cube is 1 centimeter. So if you look at the definition of specific surface, okay, second please. Okay, not for us, right? No audio, video. So it's they think they have to see. So a specific surface was surface area over volume. So I'm going to look at this definition, surface area to the volume. If it's a cube of 1 centimeter each side, please visualize it has 6 sides, that's 6 over there, and the surface area or the area of each side is 1 centimeter square. So that's the surface area. Volume of the cube is of course 1 centimeter cube. That's the specific surface. If I look at this, it comes out to be 6 per centimeter or 0.6 per millimeter. If I go down, and if the cube is now 1 millimeter each size, remember going down is in fact I'm reducing the particle size. I'm looking at an analogy such that the cube is something analogous to the particle size, and going down the cube, smaller the particle size. Let's look at the specific surface. I have now 6 times 1 millimeter square, that's the area, over volume which is 1 millimeter cube. Now the specific surface which was 0.6 now comes to 6. Okay, if I go down, and similarly if I have 1 micron each side, the same cube is now has a specific surface of 6,000 per millimeter. Okay, remember it's a huge difference. So it's a huge difference means, let me explain this. Huge difference means that the smaller the particle, it has a greater surface area. the surface area starts to increase, meaning the surface of the particle which is exposed to sunshine is now more. Or if I would like to coat this particle by water, a thin film of water, if I like to brush this with water, I just, I need greater amount of water for particles which have greater specific surface. This in fact is an important thing when we want to look at the activity of the soil. Okay, so in order to look at this activity, I would like you to look at the three minerals, the three important minerals which are montmorillonite, Alight and kaolinite. Remember, Alight is in between. So the diameter in terms of nanometer is typically, we're looking at crystals, so stacks of each 2:1 to make one large crystal. So the diameter of this crystal is approximately 100 to 1000 nanometer. So you're looking at 2 orders, 2 to 3 orders. Okay, Alight is 10,000 nanometers. Again, I would say 3 or 4 orders. It's running out to be similar. Montmorillonite, Alight probably have a diameter going down to kaolinite. All the three have a diameter which is again, varies between, within an order. As a thumb rule, I can say the diameter is approximately similar compared to the thickness. Look at the thickness. The thickness varies by 1 order over here, but over here again by 1000, so 2 orders. Over here, in other words, if I would like to find out the specific surface of this, I have specific surface of montmorillonite, which is the smallest particle, okay, considering diameter and thickness, to the kaolinite, which is the largest particle. In other words, montmorillonite will have a greater affinity for water compared to kaolinite. If I want to rephrase this, montmorillonite will be more active compared to kaolinite. In fact, this is important for us, for engineers, because many engineers say, come on, I'm not going to look at the clay minerals. I don't have access to electron microscope. I don't have access to XRD. I can't look at minerals, and I'm an engineer. An engineer is looking at engineering property. So he or she would be more interested in looking at the activity. So if I go if I go from bottom to top, my activity increases by a large quantity. So I have a table over here which is ZAP from a literature, and it's quite obvious over here. Montmorillonite, whether it's highly active, of course you look at this, given a chance, the difference, but going down to Alight, kaolinite, the activity starts to reduce. So rather than look at clay minerals, people say, okay, let's look at activity. Okay, and activity is defined as the ratio of plasticity index by clay content. We looked at this definition before. So that's activity. So people say it's easy for me to measure. So I can speak about which clay mineral it would be based on activity. That is easy. Having said that, if you don't have a dirty mix of clay minerals, the clay mineral is easy to identify in terms of these three. But many times nature gives us a lot of surprises, and you may have a mix of clay minerals or something which is not so common. But in majority cases, engineers really get away by finding out the activity. Let's go to next slide, please. It leads to an important term definition, which is adsorb water, that's AD water, and absorb water, AB water. Remember, when we do water content determination, we always put the oven at 105 degrees. That's because we want to remove this AB water, absorbed water, which is freely available water, as opposed to adsorbed water, AD water, which is chemically bonded water. And we will look at this chemically bonded water in the next 1 or 2 slides. The question is, how is this water AD adsorbed on the surface of the clay mineral? Some people like to put this as, give a very nice name. They call it as diffuse double layer, DDL, but you're not going to look at those things today. What we say is how this water absorbed, how is this layer formed. Okay, in order to understand this, there is, we should be aware, water is dipolar. If you look at water molecule, it's H2O, 2 hydrogen and 1 oxygen, or H and OH. So H is positive, OH negative, and water is, we call it as dipolar, meaning overall the molecule is neutral because H, OH balances out, but they are skewed towards the far end of the molecule, meaning H is one end, OH is at the other end. So it's like a magnet. Let's call it a mini magnet. So in other words, overall it's neutral, but dipolar makes it one end positive, the other end negative. So because of this dipolar thing, let's see how this water gets absorbed or attracted to the clay mineral. Okay. So the very first one is the three out of those 3 attractions which occur. The first one is electrostatic attraction, which is not so strong, but because water is dipolar, okay, so it gets attracted to the negative surface of the clay crystal. Remember, clay has a positive silica or alumina at the center, the surface is negative, which is HOOH. So water gets attracted because of itself being dipolar. I can also say clay is also dipolar, okay, but clay also has negative at the surface. The second one, which is much stronger bond, okay, is the hydrogen bond. So hydrogen of water gets attracted to oxygens or hydroxyls on the surface of the clay mineral and forms hydrogen bond. This is very strong. So that this contributes to the greater attraction. So if you put your oven, the heating oven to 105, you can never remove this water, never ever, unless you increase to 200, 250 and start shooting up, then you are able to remove this water. The third one is other cations in the water. So because this water which is gets attracted to the surface of the clay mineral, the water itself may have some freely available cations in it. So some positive ions may be present around the water. Okay, these positive ions which are already attached to the water which now goes to the clay mineral, carries these cations. So that's another access to the attraction, or the access to the cations which bring in. So these water bring in excess cation to the surface of the clay mineral. This is important for us to understand. The excess cation which come in, okay, let's call them as floating cations because they are floating in the water and they are now attracted to the clay mineral. These cations, give example of these cations, can be calcium, sodium, potassium. So they are available in water. Okay, I mean they would be added in water. I apologize, they are not available in water, but if they are available in water, they get attracted to the clay surface. Okay, and they get this AD water, so they get adsorbed water. Now the cations which are attracted, okay, have a tendency to replace the existing cations in the clay. For example, if there is sodium, over here I have an example of sodium. A sodium which is present in the in the clay mineral, I can replace this by potassium. So if I have potassium coming in, it replaces the sodium. This has far-reaching consequence on the property of the clay. It changes the property of the clay, and this ability to exchange the cation of the clay by a cation which comes out, the cation which we call it as floating cation. Okay, this ability is called as the base or the cation exchange capacity. Okay, so it's important term to be used if the cations are exchanged, okay, within the clay mineral. We look at this cation exchange in the next slide as well. Okay, look at an order. Okay, I always tell people, except for hydrogen, if you go from left to right, if the charge is the same, so lithium, sodium, except for hydrogen, potassium, this is, sorry, this should be NH4 positive, so it's not 4 plus, 4 should be suffix somewhere here. Okay, let me zoom in to correct this. I'm not sure if I can have a white pen. This is 4 over here, okay, not visible. It should be N, my drawings are very poor, NH, and there's a 4, NH4, and there's a positive over there, okay. That's how it should be. So NH4, if you go from left to right, I always tell, you know, our research students, you know, as in road traffic, if you have a heavy vehicle, the fatter you are, the more powerful you are. So with the same kind, you know, the same charge, as you move from left to right, the bigger you are, you can replace the smaller one. So it has far-reaching, you know, consequence. And plus, I always tell them, you know, this is NH4 positive, it's 1 plus, okay, not 4 plus. I always tell, you know, further on, this is 2 plus, 3 plus, meaning there's another statement. If there are more crowns in your you know, more I would say, not more diamonds in your crown, or more, you know, pearls in your crown, meaning this is 1 diamond and more diamonds, the richer you are, more powerful you are. So over here, the fatter you are, the stronger you are, the more powerful, and going on to more richer you are. So in other words, a richer person will easily replace a poor person and a thinner person over here. In other words, calcium can easily replace sodium. Okay, I hope it's easy to remember this way. This has far-reaching consequence. So if I have a clay which is very swelling, you know, which has sodium ion, all the black cotton soil, which, you know, you reduce its swelling potential by adding lime. What is lime? Lime is in fact calcium carbonate. So this calcium from the lime adds to the black cotton soil. Black cotton soil is our montmorillonite clay. So you add this to the montmorillonite clay to reduce its swelling potential. So from left to right, the swelling potential is bound to reduce, because now the heavy ones or the stronger ones occupy the space. Okay. Let me move on to the next slide, please. Okay. We're coming towards the end, so probably if you have any questions in the next 5-10 minutes, we'll give you about 10 minutes to, you know, to ask questions. So you're coming towards the last 2 or 3 slides. These slides are to help understand the difference between structure and fabric. You know, it's important to know that for minerals like clay, there is a huge difference between structure and fabric. Now, usually, fabric we say fabric is in fact is a new term which came out only a few decades back. Fabric we represent to the arrangement of particles. So we look at how the clay crystals. Remember, we can't look at individual 2:1. We can only look at the stack of crystals. So when we look at the crystals, we look at how the crystals are arranged. Okay, looking at the arrangement. If you're just looking at the arrangement without looking at the interparticle forces, meaning just the arrangement, you call this as fabric. Okay, so you're looking at clay fabric. A structure would include the interparticle forces as well. Okay, that's structure for us. So previously we used to call this, you know, everything. So interparticle forces and the arrangement as structure. This is true. Structure means arrangement and the forces. But if someone just wants to speak about arrangement, because there is a class of engineer who would like to just speak about the arrangement, because this arrangement heavily controls the mechanical behavior of the soil. So once we do this compaction test at some time in the next lecture, we would be interested in the arrangement. So arrangement, for those people, fabric is important because they just like to look at arrangement. But in case you are keen on arrangement as well as the particle forces, you would speak about structure. Okay. So let's look at thing. We say, you know, the clay particles, you know, they can arrange in two manners, broadly over in two manners. Okay, if they have a very strong attractive force, you know, meaning this, we will look at this again later. If the clay particles have less of water, available water, they will have more attractive force because the negative charge is not fully developed. Again, we will look at it, you know, later, but for the time being, if you just visualize that there is a set of clay particles which have very strong attractive force and a set of clay particles which have less attractive force. The ones which have strong attractive force will tend to flocculate. So that's over here. So if there is a net attractive force, the particles will tend to flocculate. Otherwise, they tend to disperse. So there are two arrangements, flocculated and dispersed. And remember, these two are just arrangement of the particles. So we are only looking at fabric. So these two represent the fabric. Okay. So we're looking at fabric in a way that the flocculated was one. Please look at this one. So you have a flocculated, without looking at the cartoon which is over there, there is a flocculated fabric and a dispersed fabric. A flocculated fabric is like you say, has more interparticle attraction. So this attraction makes them in a random, the arrangement is random because each one likes to be attracted to the other. It's randomness. So a lot of people getting attracted to one person. So that's the we call it as flocculated, randomness. Please look at these lines which have been drawn. Each one of these lines, traditionally they represent a clay crystal. Okay, so one of the crystal is this way. So if this is crystal, we say the surface of the crystal is negative and the center of the crystal is positive. Remember, it's stacking of them. So centers always remain positive, surface is negative. But in case the negative is not fully developed, so they have a large amount of attractive force which makes them arrange either edge to face. So if you look at some of them, so this is face, for this fellow this is face, and for this fellow this is edge. So over here you have an edge to face attraction. It's much clearer over here, edge to face. There can also be edge to edge configuration. Let's see if we can find some stacking edge to edge. Yep, over here it's a nice configuration for edge to edge, meaning two edges are, you know, attracted. So that's edge to edge. In all, you will see a lot of mismatch arrangement. Okay. Compare this to the dispersed fabric. The dispersed fabric, what you see is, you know, there is some amount of regularity coming up, or I would say the randomness is lot less. All these lines which represent clay crystals, we call them as sleepy lines. You know, they are sleepy. So probably half of you who are in the class probably have this nature by now. You know, it's 45 minutes to the class, so half of you would be sleepy. So this probably represents dispersed fabric, you know, sleepy lines. There is a arrangement over there. So the randomness is less. All these lines are you know, stacked nearly close to one on top of each other. Okay. So this configuration is face to face. So each face is, this looks much clearer. Face of this is now aligned to face of this. So this is face to face. Okay. Most of natural clays which you find are flocculated, are as per the figure on the left hand side. But if you have clays which have been deposited due to sedimentation, you know, sedimentary nature, so historically the geology of the clay shows that the clay has been deposited layer by layer. So most of the deposit would occur in dispersed manner. Okay, to give you an idea, when you do a laboratory test for hydrometer analysis or for pipette analysis, well, you add a deflocculating agent. So you add an agent such that the clay is deflocculated. So if your clay is something like this, with time, if you are deflocculated, it becomes more of this manner. The purpose is to, the attraction, reduce the attraction between interparticle or intercrystals, such that you can get a better estimate of your particle size. Okay. Again, this dispersing agent which you add into the soil, it's very strange. I must say, I shouldn't use the word strange, but it's very interesting to see that many of our research students, when they want to produce clay which is dispersed, so they add this dispersing agent to the clay slurry and then consolidate this, because they say, so we want to do triaxial test or some test on this soil, but we want to prepare in dispersed because we want to mimic the nature, how the nature has deposited the soil. That's fine, but to give you an idea, to prepare this kind of clay, this thick, this kind of clay would take a month. But to prepare the other clay, which is dispersed, would probably the same thickness, approximately 30 to 40 centimeter, would take about 2 to 3 months. So you're looking at a time frame of at least double. So that's something many of us have to be careful about. Okay, we are on to our last slide, and thankfully it's still not less than 15 minutes down the class, so it's good. The last slide speaks about granular soil. Granular soil, is, we say, sands. Take an example of sand. The mechanical behavior of sand is governed by the gravitational forces, because the interparticle, there are no forces, there is no the attraction between the particles, because the silica, remember the granular soils are also made of silica, they also have silica, but the silica in granular soils is inert, it's not reactive. It makes us think that if you're looking at the arrangement of the particles in granular soil, okay, should we call it fabric or should we call it structure? Remember, structure includes arrangement as well as bonding as well as interparticle forces. So, but in granular soil there are no forces. That is why many people, they say, when we speak about granular soil, although you speak about just the arrangement, you do mention my soil structure of my sand is so and so. Although you only speak about arrangement, it's only because sands or the granular material have no interparticle forces. Lastly, there is one called, if you look at this carefully, volume of voids in coarse grained or granular soil is much less than the volume of solids. Okay, which is not the case for fine grained or clay kind of soils, because of which the void ratio of clay soils is larger than the void ratio of granular soils. Okay, I do not know why I put this statement over here, but probably it's interesting to note this. Okay, so we are towards the end. Any questions? We have someone from TKMKL. Okay, start introduction.
Good afternoon, sir. Can you hear me?
Yes, you're very audible. You're very audible.
Sir, I am a student of TKM Engineering College. I have a doubt. Bentonite clay, which is used for stabilizing of boreholes, is it same as montmorillonite?
Yes, it is the same. Yes, it is the same. Bentonite is the trade name, commercial name given to the same clay.
So they are both the same. We are doing the same process of controlling swelling and all in bentonite as well, when we are using it for the purpose of okay, sir. And one more doubt. You use the term diffused double layer in one of the slides. Can you please explain it?
Yes. Okay. This term in fact is very popular. It is very popular from IISc Bangalore. What they say is that at QEEE water, once it gets once it chemically bonded to the layer, that the attraction of the water to the decreases with distance away from the plate. So if I have a clay crystal, if I move further from the clay crystal, what I see is the attraction force decreases. In other words, the water which is surrounding the clay crystal, the thickness of the film layer is about distance away. Thickness of this layer is the diffuse double layer. Okay, the camera, my camera seems, so I do not know whether you can see me. I hope you can visualize this. You have a clay crystal. You're moving distance away from the clay crystal. Distance away. You see that chemically bonded water has less force, because this attraction force decreases with distance away from the crystal. But to the layer bonded chemically bonded exists, called this layer is double layer. Okay? Okay? I hope this was I was able to explain this.
Yes, sir, it was clear. Thank you so much.
You're welcome. You're welcome. Okay, we have AIM. Yes, please. AIMT teacher, please, we are with you. Hello. They can't see us, right? I guess we can't see anyone on the screen, anyone saying anything. You have a question, please? Okay, there is no audio coming from your end. I apologize, no audio coming from your end. Okay, DCRU, we'll come back to you again, but right now we are with DCRU.
Good morning, sir.
Yep, good morning.
Actually, I wanted to download your presentation. You have said that it is downloadable, but I am unable to download it. It is denying the permission.
Let me check again, because we have right clicked it. Okay, someone here is helping me. Yes. If you on the slide, if you click anywhere on the slide, right click it, there would be a window, pop-up window. If you right click anywhere on the slide, a pop-up window will probably show something like download.
No,
Download
sir,
this
not there.
document.
No, it's not there, sir.
Okay, for us, it shows that viewers can download this document.
In our screen, it is showing the viewers permission is denied.
Okay, what I'll do is I'll redo this thing again. So I'll unload the document and then load again. Let's see if this works.
Okay, sir.
Actually, it's not me doing it. Someone next to me who is doing it. So.
Thank you, sir.
Okay, can you please retry again?
Yes, sir.
Is it working?
Yeah, okay, now it's working, sir.
Okay, good. Thank you. Any question, please?
Thank you very much.
You're welcome.
Okay. Okay.
That I think they are taking care. That the support people they take care from Chennai. Oh, sorry. Yes, please. We are with you. AIMT. AITM. Just there is no audio, please. Can you wave if you can hear my voice? Can you hear my voice? Because I can't hear you. Can you wave if you can hear me? Okay, so that's good. At least one way we can, communicate. But I can't hear anything from your end. Okay, I have a suggestion over here. If you can put the question in a question tab, that's the chat. If you put the question in the chat, I will be able to read it and then probably spell it. It says VECAP sound was not audible throughout the session. The additional water content shows more swelling shrinkage. Have they finished writing? Okay, I think the question, I'm not able to figure out the question completely. It says the additional water content shows more swelling and shrinkage. If I'm able to understand your question clearly, it means that the additional water on the clay mineral induces more swelling and shrinkage. So I think the question continues, shrinkage in some montmorillonite clay. Okay, so montmorillonite clay, if it has more water content on its surface, yes, it induces more swelling and shrinkage. Your question is very right. It's because of the additional surface area which is available, as well as the weak van der Waal forces which exist. So all this in combination makes it more prone to shrinkage and swelling. Okay. I hope this was your question. Okay. Thank you. You are on to our nearly 12 o'clock, and I think I have to cut off right now. Otherwise, people will not. Thank you. Thank you. So we'll continue next time. Okay, next week. Thank you. Goodbye.